These days, you often hear or see headlines saying that quantum computers are going to break Bitcoin. So, is it true? If you don't understand how this technology actually works, it's easy to get manipulated by fear or false hope. In this video, we're going to dive into the underlying logic of quantum computing. So, here comes the first question: what is a quantum computer? Well, the computers that we use, the classical computers, or the phone that we use, or the servers that are powering the internet, they are all built on bits. A bit is the smallest unit of information, and it can be 0 or 1. You can think of it like a light switch. It's either on or off, and everything digital is built on bits. However, at the quantum scale, the world of atoms, electrons, and photons, physics behaves very differently. Quantum bits, or what we call qubits, they can exist in a state called superposition. That means a single qubit can be 0 or 1 or both at the same time until you measure it. It's like the Schrodinger's cat. It's both alive and dead until you open a box. When you have multiple qubits, they can also become entangled, and this creates a strange quantum link where the state of one qubit instantly affects another, no matter how far apart they are. And Einstein famously called it spooky action at a distance. Thanks to superposition and entanglement, n qubits can represent 2 to the power of n possible states at the same time. That means 10 qubits would equal to over 1,000 possibilities, and 50 qubits would equal to over a quadrillion of possibilities. With that being said, the main difference is that a classical computer solves problems by checking possibilities one by one, while a quantum computer can explore many possibilities in parallel. You can imagine there are 100 doors and 100 keys provided for you to unlock each door. If you are a classical computer, you have to try each door one by one. So you have to try it 100 times. But if you are a quantum computer, you can try all the doors at the same time because it happens in parallel. This makes quantum computers incredibly powerful for hard problems like cracking complex encryption, simulating molecules for drug discovery, optimizing AI, or modeling financial risk. This is exactly what people are worrying about. Quantum computers could break today's encryption system, especially the public key system like the RSA or the ECC, which is the elliptic curve cryptography that Bitcoin uses. So how does public key cryptography work, and how can quantum break it? Public key cryptography lets you securely talk to someone you've never met before without sharing a secret password first. It's like when you're visiting your online bank using the logged HTTPS connection. You securely communicate with the bank server without meeting it, and you don't need to share a secret password. This requires 2 mathematically linked keys: a public key that you share with everyone, a private key that you keep completely secret. The system is designed around one-way math problems, easy to do in one direction, extremely hard to do it in reverse, meaning that you can derive your public key from your private key, but you can never trace it back. Again, the system is designed that way so nobody should figure out your private key. And again, the 2 main types, as I mentioned before, is the RSA or the ECC. On a classical computer, if you do want to figure out somebody's private key using the public key, again, you have to try all the possibilities one by one, and even with the best algorithms, it would take you billions of years to do, so it's impossible. But quantum computers they're made to do these. So using Shor's algorithm, you can drive the private key from the public key. Now, there is a catch because this is just theoretical. Today's quantum computers are extremely fragile. Qubits need near perfect conditions, usually at temperature close to absolute 0. And they are unstable, they're noisy, and they can only maintain coherence for microseconds. One of the most advanced chips right now is the Google's Willow, and it's released in 2024. It has 105 physical qubits, but only a small portion of the qubits are actually used in computation. Using this, in its key error connection experiments, Google has demonstrated 1 logical qubit. Now, earlier this year, according to Google's research, it was published, I think it was in March. Yeah, it was published in March. And they said that breaking Bitcoin's ECC would require roughly 1,200 logical qubits in an optimized setup. So again, we can only make, right now, we currently only have 1 logical qubit. And to break ECC, we need 1,200. And that means right now we're still in the very, very early stages. So is quantum computing a threat to Bitcoin? Yes, eventually it is, but not right now.